Okay, and Oscar has a question. How do we do inverse Laplace transform for 3C? I like this question. So if you go to EM3 here, apologies to those of you that have handed in the project already about the fact that there's still a question about it. That's fine, Oscar, for you asking. But I just hope that my answer has a bit of insight in general for life. So your question is, how do you do an inverse Laplace transform? For example, how do you know that the inverse Laplace transform of this guy is this guy? Well, it's just, the question is like asking, how do I know that the solution to the equation 8 plus x equals 10 is x equals 2, right? So one way you can say this is I subtract here 8 and I scratch away the 8 and then I get a 2. That's one way to know the solution. The other way is to answer my question, how do I know that the solution 8 plus x equals 10 is x equals 2? I stick in a 2 here and I see it satisfies the equation. Now, similarly, to know that this is the inverse Laplace transform of that, what you need to do is you need to do the Laplace transform of this 0 to infinity e to the minus theta t dt and get that. Okay, so Laplace transforms have and rely on the fact that there is a one-to-one correspondence between a function and its Laplace transform. So you're actually given the inverse Laplace transform. Of course, with spare time on your hands, you can look at Laplace transform tables. You can do partial fraction expansion to this guy, which would be the standard way. Or you can do integration in the complex plane and calculate residues and stuff like that. But you don't want to do that. I hope that helped. Okay? Is that all right? All right, sure. More questions of that sort? All right, so let's get back here to the self-study guide, and we stopped in MC3 section 3.5 invariant distributions. I mean, I thought Tuesday that we'll finish it by that time, but we didn't. That we'll finish it Tuesday, but we didn't. So an invariant measure or an invariant, it's not a distribution at this point, it's just a sequence of numbers, which you just call a measure. And if your finite state space is a vector, is something that satisfies this system of equations. And so it's on the way to being a stationary distribution, okay? And what this theorem spoke about, we spoke about this here at length, is the relationship between this lambda, which solves this, or which satisfies this, not which solves this, and mu, which does it with the embedded Markov chain. And you saw here that mu is proportional to lambda with the rate of q, which kind of makes sense, because if you think about it, think of the realizations of discrete and continuous time Markov chains. So, or say, think of a realization of a continuous time Markov chain. Sorry, I know this is messy, which jumps here between states, and the embedded chain kind of goes from this state to this state, 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 or maybe there are other states, etc. So the measure for the embedded chain would not take into consideration these durations, which, you know, have varying means inversely proportional to this qi. Okay, and that's how you kind of, that's, well, an interpretation for this. Okay, let's go to the next theorem. Suppose that q is irreducible. Okay, so there's a single class in the embedded Markov chain, or in Q itself, and recurrent. So you return to each class to each state with probability 1. So if there's a single class, if one state is recurrent, all states are recurrent, because recurrence is solidarity property. Then Q does have an invariant measure, which is unique up to scalar multiples. So this says that an irreducible recurrent continuous time Markov chain has an invariant measure. It's still not a stationary distribution, but it's an invariant measure. And again, measure, we'll speak about measures next week, but in this point, think about it just as in terms of, in this measure is a sequence of lambdas, okay? That's what it is in this discrete state space. Okay, let's go to the next one. Let Q be an irreducible Q matrix, okay? So Q is a Q matrix, a generating matrix, and the following are equivalent. So this is an equivalence between 1, 2, and 3. Every state is positive recurrent. Some state is positive recurrent, fine. So if one state is positive recurrent, then any other state is positive recurrent. And Q is non-explosive and has an invariant distribution lambda. Q is non-explosive, and explosive is kind of not the focus of our course, okay? At least from my perspective, explosives is a bit more of an esoteric thing. Don't think of explosive as just a process going to infinity. Think of explosive as this type of thing happening, okay? After some finite time, okay? So this is kind of, these are 3 regularity properties. So this is one characterization of positive recurrence, okay? Of an irreducible matrix. So positive recurrence will be if it's not explosive. So we're not speaking about the explosive case because they're kind of not interesting when you're thinking about long-term behavior because this thing finishes. And there is an invariant distribution. Okay, so if you have an invariant distribution, you're positive recurrent and vice versa. Now remember, positive recurrence was that you reach each state with probability 1, that's recurrence, but the expected time of return is also finite. Again, we're reading here a section that we're supposed to skim, okay, and that's pretty much what we're doing. So I'm skipping the proofs, and they're beyond the level that you need for the assessment of this course. Okay, and let's look at this one. The next result justifies calling measures lambda invariant. Okay, so let's look at these 2 equations. So let Q be an irreducible and recurrent, let lambda be a measure, okay? Let S be some time, S is some given time, okay? So 2 things hold. One is lambda Q equals 0, okay? And that was how we define an invariant measure. But this one has a bit more of a meaning. So what is P of S? P of S is the matrix with entries, the probability of x of s equaling I given at x of 0, j, sorry, I should say, equaling I. Okay, that's P of S, okay, for all ij in the state space. Okay, that's the transition probability matrix of the, you could say, the discrete time chain that takes jumps at size s, or it's just the probability of going from state I to state j. You know how to compute these things, say for finite matrices, you do e to the power q s, okay, for finite state spaces. That's what PS is, okay? So you would think that, and you know well from discrete time Markov chains that you have a left probability vector and you multiply it by p, you're getting the state of at the next time, or if you multiply to p to the power n, you're getting here not the state but the distribution of the states times pn. Okay, right? So this can be the distribution at time 0, and this would be the distribution at time n, discrete time n. Okay, now to be invariant, what does invariant means? Doesn't vary. Okay, so it means that if you started with some measure at a given time, then after some multiplication of p's, you're still in that measure. So you're here. Okay. So what this means is that there's just an equivalent definition of an invariant measure. An invariant measure is something that you can propagate. You would propagate these probabilities, but maybe these measures, maybe the measure isn't just probabilities, maybe it's just a sequence of numbers, and you stay with the same lambda. Okay, that's what we mean here. Okay, and at last, theorem 356, let Q be an irreducible non-explosive Q matrix. So we're not speaking about explosions here. having an invariant distribution, if xt is Markov lambda q, so that means so now, you know, lambda is an invariant distribution. So if you start with probability distribution lambda, then after some time, you get the same. This is also, so the probability law of this sequence of random variables is described by Markov lambda q. Okay, I mean, if I tell you you've got a sequence of random variables, that's what we call a stochastic process. That's what this course was about, right? I tell you the sequence of this random variables is distributed according to Markov random q. You know what that means now, okay? So if you shift time s units forward, then you're also going to be Markov lambda q. Now it's obvious, you know, you're going to be Markov q, and here you're going to have the same lambda. So the reason that happens is because you've propagated these probabilities and your supposed new initial distribution at time s did not change, okay? In general, if you would not start with initial distribution, which is the invariant measure, okay, then you would not be here with the same initial distribution, right? Because the process would still not be in equilibrium. So starting at the invariant measure or the stationary distribution, if you'd like, okay, is like, so starting the process at the stationary distribution means it's stationary from the go, from start. Okay. Let me convert this into something kind of much more applied, just so you kind of get a bit of a feel for why these things might be important. I mean, say that you take this MM1Q, okay, which is just a neat, simple example of a continuous time Markov chain. Okay, this MM1Q here. Okay, a birth-death process with constant lambda and constant mu. This MM1Q certainly did not start at its invariant distribution, right? What distribution did we start this MM1Q with? So this MM1Q, this you're seeing here realization of a process that's Markov something Q, and I'll write Q minus lambda lambda minus mu plus lambda lambda mu, and these things continue forever. That's the Q. So what did we start with? What initial distribution did this realization start with? What do I put there? So what distribution did this Q start with? I mean, this specific realization of xt, which you see a plot of here. So we started it with an initial state Q0, which we ran to be 20. Okay, so we started it with a distribution that you might call, say, delta 20. Somebody said that in the chat. 20-ish people. 20-ish people. Thank you. Yep, you start with delta 20. Okay. Now the meaning is, if I would now want to see how this Q behaves in the long run, and I would say run a simulation for these 200 time units and do a time average. Okay, so let's not even speak about let's just say I want to do a time average. So the way I would do a time average here, by the way, just so you see it, I would do like X hat bar would be the 1/200 divided by the integral of 0 to 200 x of t dt. Okay, where x of t is the realization, right? I mean, I would just calculate the area under the curve here. That's what you do. Okay, and I would divide that by time 200. This is an average of a continuous process. Okay, but it's a sample average. It's a sample average. Okay. Now, the expected Q length here in steady state should be the expectation of this geometric random variable, which happens to be rho over 1 minus rho. Okay. However, this X bar here, which is supposed to estimate and give me something like rho over 1 minus rho, right, which should be 0.7 divided by 1 minus 0.7, okay, something like over 2, okay, there's an expected number of people over 2, is going to be a biased estimate. Now, the reason it's going to be a biased estimate is because this sequence of random variables is not distributed according to the stationary distribution. Okay, so there's this kind of initial time where this is not the stationary distribution. Now, what do you do if you want to simulate it like that? Of course, you could have told me, you could have said, hey, just start it at 0, all right? But 0 is also not the stationary distribution. So what I could have done is I could have started it at the stationary distribution, which is this. So for the initial random variable, I could have chosen a geometric random variable. Okay, so I would have chosen a geometric random variable of where to initialize. In that case, this would have been a stationary process, okay? And this estimate would be actually an unbiased estimate. I mean, it still has some variance because it's a sample, it's an integral sample average, but it would be an unbiased estimate, okay? Now, often I wouldn't have, if I'm actually simulating a system, I would never simulate an M1 system just like that unless I'm kind of just teaching, because I already know all these properties, right? I mean, here it is. I mean, I know a whole bunch of the properties of the process. I mean, by the way, I don't know all the properties. Like if I want to know the correlation between this point and this point, I don't know that. I mean, it's a complicated sequence of dependent random variables, but I know a lot of these basic properties. So you'd often simulate much more complicated systems or systems where you don't know stuff for. So what you would do is you'd often run the simulation for a while and you'd call that the warm-up period, okay? And then you start calculating the sample averages just from a period afterwards. That's just a thing to know. Because you don't have the luxury of starting the process at stationarity as you do in this thing. Okay. All right, and ask me if there's anything. So we're here. Skim section MC3, convergence to equilibrium. Okay, there's quite a lot to know about convergence to equilibrium of discrete time Markov chains and continuous time Markov chains. And should we have focused on other things in the book, one aspect that this is important for example, is in this field called MCMC. Has anybody heard about MCMC? Any Bayesians here in the? Somebody say that it's heard. You don't have to know what it is exactly, but has anybody heard about MCMC? Oh, in STAT3004-STAT7304. Yes, thanks, Oscar. Great, which is probably taking place this semester. Who's teaching that, Oscar? Alan and Dirk. Okay, good. You're in good hands. All right, so MCMC. So Monte Carlo Markov chains. I mean, the general idea of MCMC, it's a way of, so I'm just giving this here as a motivating example. Monte Carlo Markov chains, it's a way of generating random variables from a given distribution, where the way you obtain the distribution is you actually construct the Markov chain and you simulate for that Markov chain. So it's Monte Carlo Markov chain, or maybe Markov chain Monte Carlo, or maybe Monte Carlo Monte Carlo. No, we don't know. Or maybe Markov chain Markov chain. No, I'm joking. It's Monte Carlo Markov chain, or maybe the opposite. Okay, so Monte Carlo simulation, random simulation. Okay, well, so what you're doing there is, you know, your given input is pi, is some stationary distribution, but you don't treat it as a stationary distribution. You just need to simulate random variables from this distribution. Of course, in our case, you know, pi is going to be only finite vector or maybe countable, but in MCMC, it's actually going to be a continuum often. Okay. Now, the way you actually get this pi is, it's going to come from some Bayesian thing. So it'll be the posterior distribution. So there's all this other story where, you kind of, that's how you got the pi. But maybe you got it elsewhere. So it's applied to Bayesian analysis where you want to sample from a posterior distribution. That's the most common application of Monte Carlo Markov chains. Okay. So what you do in MCMC is you construct some p. Of course, there are many p's that would have that pi, but you construct some p such that pi p equals pi, okay, and some pi I equals 1, okay? So you construct this orange p, which will have that stationary distribution. And you don't construct it explicitly. What you do is you often run something like the Gibbs sampler or the Metropolis-Hastings algorithms, or another algorithm that actually implicitly has in it a Markov chain where you're guaranteed that in equilibrium, this Markov chain has pi. However, your big problem with MCMC is that it's just like I had before with the MM1Q. If this is your time, okay, and you do this often in discrete time. I mean, this doesn't have to do with continuous time Markov chains, but the story is the same for both, and that's the section we're in: convergence to equilibrium and continuous time Markov chains. So you do it, and up to a given time, well, what you're going to do is you're going to let this thing run, okay, and you would throw away this bit, just like I spoke about before, the warm-up period, and then you'll start using this as data, and you'll sample points from this data, okay? And you'll call these were going to be random variables according to pi. Okay, the key idea is that this is going to be like from your posterior distribution, and then you can compute all kinds of Bayes estimates, etc. Now, the reason you're throwing away this is because you believe that, you still haven't, quote, reached your stationary distribution. You don't have that luxury of starting at that stationary distribution because it's hard from the first go to sample from pi. Unless, by the way, you can do all kinds of schemes called perfect simulation. I mean, this is a whole research field, and there's a lot happening there. Okay, so the big question in MCMC, or one of the big questions, is how big should this capital T be so that you throw away this data? Okay, I mean, you don't want to run for 5 days and only then start sampling. Okay, and at least here we're going to see it in a much simpler setting. Well, that's kind of somewhat described, or how you converge to this equilibrium. Okay, so how does your distribution converge to the stationary distribution? That's kind of the general question. Okay, so we start with this lemma where, and this is a section we're skimming through. So you've got a Q matrix with semi-group P of t. Okay, you could just treat that as P of t is e to the power qt. Okay, if this thing exists. Okay, then this just means that your differences, you have kind of a uniform bound on the decay after h time units, which is exponential with the rate of qi. Okay, that's what this is. I mean, this lemma is used as input to the other theorems. Okay, so I mean, in general, your differences in probabilities Pijt and Pij after time units, are bounded below by exponential decay. Okay. So here is theorem 362. So let Q be an irreducible. Again, we're speaking about these nice Markov chains, irreducible. Okay, I mean, if you have other classes and you'll be that are transient, then you'll run into them. Or if you have multiple classes and you have the stationary distribution depends on which class you're in. So we're speaking about the nicer case. It's irreducible. We're not speaking about explosiveness. Q matrix semi-group P of t just means we have the P of t is e to the power qt if we'd like, and our invariant distribution is lambda. Okay, then this is important. Then Pijt converges to lambda g. Okay. First of all, you converge to the stationary distribution. Okay, now this is where I'm only answering your question from 1107 now, Nick. So you asked me, so an invariant measure isn't a stationary distribution? Okay, so two answers to this. One, an invariant measure can be a measure or can be a distribution. Okay, so going back to the previous section, if the measure is the sum of the lambda i's is 1, then it's a distribution. Now, an invariant measure is a stationary distribution in this kind of nice case of being irreducible. Okay, the non-explosive put aside. Okay, because then this is, you know, you could have called lambda tilde ij, or let's call it lambda tilde, yeah, call lambda tilde ij, and you define that to be limit t to infinity of pijt. Okay, it's a well-defined quantity. I mean, if this limit exists, and pijt is between 0 and 1, and this limit actually exists. Okay, so that's lambda tilde ij. So this is where, if I start in state I and go to state j, where I am after t time units as t goes to infinity, that's lambda tilde ij. What this theorem, and that you would have called the stationary distribution starting in state I. Now this chain is irreducible, so you don't care about this I, so you just call it kind of, well, sorry, keep the I there, and it's the same for all I, okay? But what this theorem says is that lambda tilde ij equals lambda j, the invariant distribution. Okay, so you converge to the invariant distribution. Okay. And you'd call it, and this is called the limiting distribution. So the limiting distribution converges to the invariant distribution. And then, okay, I actually, okay, this whole story I told you about here about convergence, it has to do with rates of convergence, but we're not saying as much on rates of convergence as I thought there'll be here. I mean, there's a whole bunch of study on the rates of convergence to equilibrium, which has to do with mixing times. Sorry about that. Okay. The next theorem says the following: let Q be an irreducible Q matrix, and let nu be any distribution. Okay. So suppose that you start with any initial condition. Okay. That's nu. Whoops. Oh my God. Any initial condition. Okay. Then the probabilities converge to this guy. Okay. And this guy is actually, so this is a different representation of what you'd call pi j. So pi j is like the inverse of the expected return time to state j. Okay. But rescaled with qj. Okay. So that's the way they wrote it here. All right. So I mean, the point here also is to know that pi j, your stationary distribution, is 1 over qj mj. That's an important thing, because say you now get an exercise where, say, this thing, ignore this, say that this is your generator matrix, and I'm asking you, please find the expected return time from state 1 to state 1. Oops, sorry. So I'm asking you, please find this guy. Please find this guy. Okay, which you'll call M1. Okay, M1. Okay, so that's the expected return time from state 1 to state 1. All right, and then what you're going to do is you're going to calculate the stationary distribution, and you'll say M1 is 1 over pi j Q1, pi 1 Q1. So you'll calculate pi 1, and Q1 is 2 in this case. Okay, that's a Q1. So you could find the expected return time. All right, let's continue. Self-study guide. Skip time reversal. That's too bad that we skip time reversal. Time reversal is a nice thing. So time reversal is you take your Markov chain, you look at backwards in time, and you get a different Markov chain. And for certain Markov chains, the backward time is like the forward time. Specifically, that holds for birth, death, continuous time Markov chains. Okay. And we're going to our last section, MC3, the ergodic theorem. So we're skipping time reversal and ergodic theorem. Okay. So Now we're not just speaking about convergence to the stationary distribution. We're speaking about how the process accumulates averages as we go, as time progresses. So let Q be irreducible again. Let nu be, this thing's called nu, be any distribution, okay? Any distribution on the state space. If xt is Markov with initial distribution nu and q, well, nu doesn't play any role here, okay? Then this thing, which I had this type of thing before, this is a time average. This is a proportion of time, okay? What you see here is a proportion of time over t time units, during which you are in state I, okay? You count every time you're in state I, okay? It's going to converge to this thing, which you can also call pi I. Okay, 1 over mi qi. And it's going to happen with probability 1. So in the measure theory videos, you'll see that this thing is called, you know, you could have written this as 1 on t, 0 t, indicator xs equals I. ds converges to this constant mi qi almost surely. Okay, to say that something happens almost surely means it happens with probability 1. Or you could have written WP1, where mi is the expected return time to state I. Okay, and that's it. Okay, that's the first part. Okay, so this is important because it means, well, even if you don't start in stationarity, don't worry about it. You could start in a different state, okay, in a different distribution that's not necessarily your invariant distribution. Okay, you can start in a different one, in any distribution. Okay, and still your time averages will converge to the right thing. Okay. Moreover, in the positive recurrent case, okay, for any bounded function f, okay, so before we didn't expect this to be positive recurrent. Now, it would have been positive recurrent if it's finite state space. Sorry, before we skip. So still staying in this state, in this first part. In finite state space, irreducible means positive recurrent. Okay. But it could have been not. It could have been, this would have also held for an MM1Q with lambda equals mu, or even lambda greater than mu, in which case mi is going to be infinite, okay? And then this means converging to 0, okay? That's what they mean here. They mean here generally that this is 0. Okay, so this first part of the theorem says if m, you can also interpret it, if mi is infinity, meaning that the expected return time is infinite, okay, which can be due to two cases, due to the fact that ti is you know, maybe always finite, but the sum p ti equaling k times k going, or sorry, I should do integral. The distribution should do density, say, of this t, you know, anyway, that this expectation does not converge, or it can be that ti actually has a non-zero probability of being infinite, as would be the case with lambda greater. But anyway, I'm saying that this could mean that you also converge to 0. Okay. Okay. Now we're going to the more specialized case where there is actually a, so I guess, yeah, when I said here, sorry, before, when I said here this was pi I mean this was pi I if mi is not 0. If mi is 0, this is clearly not pi I. Okay, so that's how this theorem is stated. Now we're getting to the second case, and let's read this. Moreover, in the positive recurrent case, for any bounded function, f from the state space to the reals. Okay, so you need a function that takes anything in the state space, gives you a real value, and f of excuse me, f of x is less than k, some kappa, and kappa is less than infinity for all x in the state space. That's what we mean by bounded function. If the, I'm not crying emotionally because of the theorem, it's just a cough, kind of got something going. Okay, so although it's a nice theorem. So the state space, if the state space is finite, then of course it's going to be a bounded function. All right. So here's an important thing. So in this case, if you're looking at bounded functions of the Markov chain, then now you can look at this guy. Okay, this was one specific example of a bounded function. I mean, this guy. Okay, the indicator function that just takes 1 in state I and 0 elsewhere. But you can have other functions. By the way, it's not okay to write here XS because XS is, you know, XS is maybe something you can't integrate. It's not a real valued thing, right? X of S can be the state. Your state can be happy, sad, or very happy, okay? Or something like that. But, you know, you can take functions of the state space. So you're looking at the empirical average of the functions. So this thing is a generalization of this thing. It's a time empirical average on the time interval 0t of this function, okay? Now, this is a beautiful thing, that this thing converges to f bar almost surely. Okay, all this probability 1 converges almost surely, converges with probability 1. The nice thing is that you can compute f bar using the stationary distribution. I mean, you knew this from before. Okay. Or your unique invariant distribution with the stationary distribution. So once you have the stationary distribution, you can compute a whole bunch of these f bars, and all you need is here, where fi just means fi means f of the state I. Okay. So just to put this in context, go back to the MM1Q, for example. Okay, for the MM1Q, if we wanted this result of the mean of the MM1Q, okay, so it's a consequence of this theorem, then we have f of I equals I. Okay, so then what you get is just this expectation. But you can also have some other cost function, right? Where you could have f of I equals I squared. Okay, so say that you're paying for customers in a squared manner. So then what you're going to get here is the second moment of this geometric distribution. And you don't need to run the simulation for it, you have it directly from this ergodic theorem. Okay, so the word ergodicity means that you can look at one sample. I mean, there's a lot of meaning to this word ergodicity, but it means, and it appears in a whole bunch of contexts. Some of you might have heard about it from Cecilia, co-lecturer in the school, in other contexts. But ergodicity means you can look at one sample path, one long sample path as you do here, and learn something about the process. Okay, and that's it. All right, I think that's almost it. Ta-ta, we're done. All right, that's your self-study guide, that's your material, you did this. Let's go to problem set, which is not here. Questions? So this is where you are, assuming that you're pretty much done with the project. If there are questions about the project, feel free to ask me. Let me just shoot this problem set to notability. All right. So the way this problem set is structured is, this is, by the way, 4 points. I'll fix this. Okay, so you get 128 points. Okay, the total, I mean, you get 128 points, so you get 28 points for free. The point of the prompt set is to do it and also prepare for the exam. So simple branching, I mean, I'm not sure what to do with the last 10 minutes, except for maybe answer questions, but you know, the prompt set speaks about simple branching processes, which were a long while ago, even when we were meeting face to face, and a bit of random walks. Okay, that we still did it, a bit face-to-face. And then you got some not very hard questions, but they're questions mostly from SP1 and a bit from MC1 on discrete time Markov chains. And then you've got two very basic questions on stochastic epidemic models. You did a huge project on that, but a few questions. And then Poisson processes, and then continuous time Markov chains, and continuous time epidemics. And that's pretty much it. That's the problem set. Are there any questions about it? Maybe you haven't had a chance to look yet. No? Okay. Any questions about the course? Anything else? Does that 128 mark system mean we can skip 7 questions, still get 100 marks? Yes, that's what it means. Yep, Nick, you can do that. So we'll just mark it all, and the algorithm for the grade to blackboard grade equals max of marks and min of marks and 100. Okay. Yeah. It's a minimum of marks and 100. Marks meaning how many marks you got. Will the exam content be similar to content in this problem set? Yes. So the answer is yes, yes, yes. Yeah. So this problem set, so your strategy, I mean, you guys, I think a lot of you worked hard on the projects, and I hope you learned something. I feel you learned something. I can only fool myself to hope you learned something. Your strategy, I believe, should be do the problem set and look a bit around the problem set. After you maybe go through the self-study guide, just a bit more beyond what you've done. And that should be your preparation for the exam. That's my suggested preparation for the exam. They won't be exactly the problem set, but it'll be similar. And I'll throw in a question or two in the exam that are slightly harder. Not with much weighting. More questions? Okay, so this is the last time we meet in this forum, this dynamic forum. There'll be a visit hour Tuesday, and there'll be 3 hours of measure theory video lectures for you to watch next week. I recommend if you're doing anything stochastic beyond this course, I recommend that you follow this. Typically, it's good to have assessment on stuff that's being taught, but we're not doing that. So that's it, everybody.
Just quickly, what's the subject next year going to be like, the one that follows on from this one?
So this year we had COVID-19. Next year we'll have COVID-20 or 21. So we'll do epidemic modeling for COVID-21. No, I'm joking. I actually, are you talking about STAT3004 again?
No, the one that follows on, the 4,000 one, stochastic.
Oh, I see. Okay. So, right. Okay. No, I thought it would be in this course next year, which I really don't know. But since I know that's not what you asked, but I think, should I teach it next year? I think what I would do is, which is not relevant for you, but maybe for your little sister or brother, right? I'll focus more on the theory from the Norris book. That's the way the course would be. If I teach it again. Now, to your question, the 4th year courses, they're actually open. The content changes from year to year in these courses. So, you know, sometimes people are teaching their convergence of probability measures. So how processes like Markov chains and such converge to diffusion processes and Brownian motion-based processes and things like that. Sometimes people are teaching stochastic calculus. Sometimes it's more specific modeling. It really varies from year to year with the advanced courses, with the 4th level courses. There is a course next semester, measure theory. taught by Artem Pulematov. I would guess it doesn't have much of a probabilistic feel to it, but still measure theory is measure theory. So that for anybody that's wishing to continue in this area, work in mathematical finance or stochastic modeling of any other sort, it's probably good to consider doing that measure theory course. Other questions of that sort or others?
So won't you be giving live lectures next week?
No, there'll be dead lectures. They'll just be in YouTube. So I'm going to put 3 YouTube lectures of measure theory focused at people that are kind of at your level, so that have done, let's say, 2 courses of probability and a bit more. Okay, so it'll be an introduction to probabilistic measure theory for people that know probability, basic probability. Okay, so three lectures like that. Expect the YouTube videos. Happy for feedback or discussion about it. Okay. Other? All right, everybody. Take care. Have a good weekend. See ya.
Yeah, thanks.
Thanks. Bye-bye.